As you can see from the objective, students will be able to find the volume of solids. So if you're in my class, this is not something new, but here's the new part with known cross sections. Now, we have been doing this, but we have only been finding volumes of solids of revolution. So we talked about when we did solids of revolution that because we are revolving, we necessarily are going to make circles. So what we're going to find out in this particular section is that not everything has to be a circular motion. So pay attention here that we're going to find the volume of solids with known cross sections. So before we begin, we're going to do our little review of some area formulas that we're going to need in order to accomplish this. So we know that the area of a square is a side squared. We know that the area of a triangle is 1/2 base times height. We know that the area of a rectangle is base times height. We know that the area of a semicircle is 1/2 pi r squared, or pi r squared over 2. And one that you probably haven't memorized that you will need for this particular unit is the formula for the area of an equilateral triangle. And that's the square root of 3 over 4 times a side squared. Remember that an equilateral triangle means that all three sides are congruent, so it doesn't matter which side you use. It's the square root of 3 over 4 times the side squared. So these formulas will be necessary for this particular unit. All right, now let's continue to do a little bit of review about finding the volume of solids of revolution. So what we have been doing by revolving, remember what we talked about, when we revolve, we necessarily either make circles in terms of x or in terms of y. Every time we revolve around an axis, we're forming a circle. So we were accumulating pi r squared, or if we had a whole, we had pi big R squared minus pi little r squared. But the whole idea is that we are accumulating the area of a circle. So we needed that formula in order to be able to get that accumulation. So this is what we were doing without holes when we had a complete solid. And this is what we were doing with holes, pi r squared. The whole deal is that because we were revolving, we necessarily formed circles. That was our geometric shape that we were forming. Now what we're going to do is we're going to form solids that don't necessarily have to be circular. So we're going to today focus, or in this video, we're going to focus on volume. It's either called volume by slicing, or it's called volumes with known cross sections. Those are the phrases you might hear when you're dealing with this particular method of finding volume. And it's really the same thing that we were doing before. So let's think about this for just a second. It's not that big of a change. We're going to accumulate the area from the low bound to the high bound. Nothing is shocking there. And we're accumulating the area of the cross section. So notice that's exactly what we were doing back up here, because when we were revolving, our shape that we were forming was circles, and the area of a circle is pi r squared. So if we follow that pattern, we are accumulating the area of the cross section. In that case, the cross section is a circle, and the area of a circle is pi r squared. So it's not a different concept. We're just going to use other geometric shapes rather than just circles. All right, so you're going to hear me talk about making a cake. That's kind of a way that I think about this, and we're forming some very interesting cakes here. So the first thing that we're going to need to be able to do, so if you look at this first example, first I'm going to show you what some of these solids would look like. And we're starting off with x equal to y squared, which is a sideways parabola, which is graphed right here. I think of that as the plate. That's what I'm going to sit my cake on. And I'm going to form a very interesting shaped cake. The cake itself, the base of the cake, is going to be in the shape of a parabola, so that already makes it sort of an interesting cake. And the cross sections, the cake that I want to make, I want to form cross sections that are squares, so that when I cut my cake, everybody gets a square. And these squares are going to be sliced, so the direction that I'm slicing is perpendicular to the x-axis. So that means when I cut my cake, I'm going to slice perpendicular to the x-axis. All right, so let's make sure that we have an understanding of actually what's going on here. Good news is you don't have to draw these. So as I said, we're going to, the parabola is the plate that we're going to set our cake on, or the form that we're going to pour our cake batter in to form the cake. So that's my plate. So you need to know what the base shape is and what it looks like and how it's formed. So in this case, we're not going to revolve the region around any axis whatsoever. We're going to put in squares. So our cake is going to be in the shape of squares. Now, from an over the top or on the top view, this is what one of the squares would look like. Think of this as you're flying in an airplane and you're looking down at the ground, and this is the base that you see. And if you were to fly over the top, this would be one of the squares. This would be another one of the squares, and that's what it would look like from the overhead view. Now, once the cake is actually formed, here it is. You can see, let's see if I can highlight. Here's the plate. Remember I said it was going to be in the shape of a parabola. Sorry, with this tablet it's hard to trace this very well. And then the parabola goes around to the other side, which you can't see anymore. But notice I have a series of squares. Here's a square right here, and it goes down. And here's a square right here, and it goes down. So what we're accumulating is a series of squares. So my goal in figuring out the volume of the cake is to accumulate from the starting value of A to the stop value of B. And in this case, we're accumulating the area of squares dx, because we're slicing perpendicular to the x-axis. That is one of your keys to success. So that would be the formula for the area of a square is s squared. And then we would have to figure out, well, how do you determine the length of a side? So we'll do that momentarily, but I just want to give you some idea. Now, what you see here is the side view. I'm going to turn the page and I'm going to show you the back view. So in other words, we're standing on the side of the cake. We're standing somewhere out here, and we're looking at the cake, and we see the side view. Now the same cake, this would be the back of the cake. If you were standing in the back and you were looking, you would see these series of squares getting larger and larger as you move away from, in this case, the vertex. Over here, you're standing from a back and a side view, and you can see the squares. So this is the side view right here. This is the top view from above, seeing a series of squares, and then this is the back view. And you can see that I have a cake that is formed by the base is a parabola, and the cake itself, when you slice it, you would get slices of cake that look like squares, and they would change in size. So we would be accumulating the area of a series of squares. All right, in the second example, now we're going to make a circular cake. So my plate in this case is the circle x squared plus y squared equal to 9. So that's a circle centered at the origin with a radius of 3. And this time we're going to make a semicircular cake. So as soon as I see that we're making a semicircular cake, I would write down the formula for the area of a semicircle, which is pi r squared over 2. And I would know that I'm going to need to figure out, all right, what's the length of the radius of my semicircles? And I'll show you that more in just a second. So when I make and these are sliced again perpendicular to the x-axis, that's really important to pay attention to. So I'm slicing the cake in this direction right here. This is the top view. So I can't really see that semicircle. The semicircle comes out, up, and over, which I can't really show you. But this is the side view. So I would have a cake that when you slice it, everybody on their plate is going to get a piece of cake. That's not a great drawing, but it looks kind of like a ghost, a semicircular piece of cake. So that's what the side view looks like. This would be what the top of the cake looks like if you're flying over it in an airplane. And then this is the side view, and this is the front view. It's not open like that. That's just the software that I used created that. So we're just having a different type of cake. All right, so when you are finding the volume of a solid with known cross sections by slicing, here is your key to success. So it's no different from revolving. We're going to sketch the base and a representative slice. The base is going to be the equation that they give you, and that's what I'm thinking of as my plate that my cake sits on. Then you're going to have to pay attention to whether the slice is perpendicular to the x-axis, because if you're perpendicular to the x-axis, you are in terms of x. You're going to have to pay attention to that. If you're perpendicular to the y-axis, you're going to be in terms of y. And when I say perpendicular to, I mean the direction that you are slicing your cake. Step number 4 is whatever shape they tell us, whether it's a semicircle or a square or a triangle or a rectangle, we're going to have to find the geometry area formula. And then for whatever variables we have in that formula, we're going to have to find a substitute for those variables. And right now, just kind of doing the overview, it doesn't make sense until you see it, but when you see it, it'll make sense. And of course, in order to integrate, we're going to need to determine the bounds, write our integral, and accumulate the infinite slices of cake that we're going to form. So in general, when we accumulate the volume, we have a starting value of A, stopping value of B, and then this part right here is just geometry, figuring out what is the shape of the cake. And we're going to accumulate it in terms of x if we're slicing perpendicular to the x-axis. And we're going to do the same thing, except if we're slicing perpendicular to the y-axis, we will be in terms of y. So let's do a couple of examples. I hope that you will see that this is really not that difficult. But if you'll do your problems the way that I'm doing mine right now, I think you'll have a lot of success. So here we go. The ones that are highlighted are ones that I'm actually assigning to you in homework, so I'm going to do ones that are not highlighted. Make a little star beside of semicircles. Semicircles are the most dangerous shape that we will form. So anytime you see the word semicircle, that means slow down, danger ahead. And you'll see why in just a moment. All right, so find the volume of the solid whose base is bounded by a circle with a radius of 1. So this is what I'm thinking of as my plate. So I'm going to sketch a circle with a radius of 1. So I'm going to exaggerate that a little bit just to give myself some working space. All right, so there's my circle, radius of 1, and this is the plate that I'm going to sit my cake on. Oh, this is not a beautiful circle. Okay, so that's the plate that my cake is going to sit on. This problem is demanding that I form cakes that when you slice them, you get semicircles. So the first thing I'm going to do when I see semicircles is I'm going to write down the formula for the area of a semicircle, pi r squared over 2. Now I'm going to put in a representative slice, and it says perpendicular to the x-axis. So when I slice a car across my cake, remember this is 3-dimensional, but we can't see the 3-dimensionality. That's one representative slice. Now think of little man. He helps us out a lot. If he's standing right here and he's looking at the cake, he doesn't see this top view that we're looking at. What he sees is something that looks like this. And it's important. I would actually draw that on my paper every time to remind yourself of what you're actually seeing from this side view, because that's the important view. We are forming slices that are semicircles. Now, we're going to accumulate pi r squared, so I'm going to start my integral. Now, visually, and we talked about this in our last unit, when we were doing circles, I can see that the starting value is -1, the stopping value is +1, and now I'm going to accumulate, remember we have to accumulate semicircles pi r squared. All right, to get that formula in there, first of all, that pi over 2 coefficient, I'm going to get it out of my way, just like we did with pi when we did circles. So now I can see clearly, now that the rain is gone, that r, I need to know the length of the radius, the length of the radius. Now this is why semicircles are dangerous. The radius is the distance from the center to one side of the circle. So when you look at this slice right here, this green slice, that is a diameter. So what you're wanting to pay attention to for the radius is the distance from the center of the semicircle to one side of the circle. So be careful, because it would be really easy to get the diameter instead of the radius. So once you identify that as the radius, it's like we did before when we were doing circles. We have the top of the segment minus the bottom of the segment. The good news is the bottom of our segment is 0. We need this in terms of x, so we're going to have to take our circle equation, x squared plus y squared equal to 1, and we're going to have to get y by itself. So y is equal to, or let's do it slowly, y squared is equal to 1 minus x squared. So y is equal to, technically, plus or minus square root of 1 minus x squared. But as you can see, we are only touching the positive side of the circle. So the length of our radius is the square root of 1 minus x squared, technically minus 0, top minus bottom. So that is the length of my radius. I'm keeping my eyes on this formula right here, because that's what we're doing. We're just accumulating pi r squared over 2. Here's my pi over 2. I need the r squared. So the r, in this case, is the square root of 1 minus x squared dx. I'll take it one more step. That becomes pi over 2 from -1 to 1 of 1 minus x squared, because I squared the square root. And then I would do the anti-differentiation and substitute the upper bound and the lower bound. That's FTC part 1 to find the volume of the cake, a semicircular cake that sits on a circular plate. So that's the first example. Now, one other thing you could do in this case is, because this circle is an even function, some of you might think about just going from 0 to 1 and doubling. You can do that, but you don't have to do that. All right, let's look at another example. And let's see, let's do one in terms of y, and then I'll go back and do another one in terms of x. So do I have an example in terms of y? Slicing perpendicular to the y-axis that I haven't highlighted. So I can't find one in terms of y that I haven't already assigned, so maybe I'll change one of these to be in terms of y, and of course I could be setting myself up for a problem that doesn't work very well. So for now, let's look at number 2, and we're going to do the problem as written, and we're going to focus in number 2, we're going to look at equilateral triangles. So we're going to find the volume of the solid whose base is bounded by the x-axis. We have to pay attention to this, the y-axis, and the line y equal -x plus 4. So let's form our plate. Remember, we always got to form the plate first to see what we're going to sit our cake on. So this problem says that our plate is going to be formed by the x-axis. So this is going to be one of the boundaries of the plate. And the y-axis is going to be one of the boundaries of the plate. And the line -x plus 4, so we're going to have a y-intercept of 4, and then down 1 and to the right 1. So we're going to have a line that looks like that. Okay, so our plate is a triangular plate. Now, I'm not picking equilateral triangles because the plate is triangular. Has nothing to do with that at all. That's just what I'm going to sit my cake on. And I see that I am creating equilateral triangles, so I'm going to draw what an equilateral triangle looks like. I'm going to put in a representative slice. So if I were standing over here and I were looking this way, this is what I would see, an equilateral triangle. All three sides are congruent. I need to know the formula for the area of an equilateral triangle because I'm accumulating all of that area. So the formula for the area of an equilateral triangle is the square root of 3 over 4 side squared. Now, the side of my equilateral triangle right here, this is the bottom. This is the segment right here. It's sitting on that segment right there. So in this case, the length of the side is the distance all the way across. So the length of the side is from the top to the bottom, and in this case, the bottom again is 0. The top of the segment in terms of x is negative x plus 4. So the length of that side is negative x plus 4. So we now need to accumulate, and I can see that we are going to begin, the lowest x value of that region is 0, so I'm going to begin accumulating at 0. The highest x value of that region is the intersection of negative x plus 4 with the x-axis. So negative x plus 4 equal to 0, so x is equal to 4. So this is an x value of 4. This square root of 3 over 4 is a coefficient that can be brought out front and gotten out of the way. So that's square root of 3 over 4. It's part of the formula for the area of the equilateral triangle. So square root of 3 over 4 side squared. And my side measurement is negative x plus 4. I'll take it one more step, and that becomes the square root of 3 over 4. 0 to 4, I'm going to square that binomial and get x squared minus 8x plus 16 dx dot dot dot, perform FTC part 1 in order to get the volume of that region. All right, so that's example number 2. Let me see if this would work in terms of y. Yeah, we can actually set up a situation where the problem is done in terms of y. So let me erase what I have here and get it reset up to do a different problem, and I'll do one in terms of y. So let's set this problem up, and we're going to, I'm going to change the problem up a little bit. This time we're going to slice perpendicular to the y-axis, and I'm going to do squares. So I'm editing this problem so that you have an example in terms of y. We're slicing perpendicular to the y-axis, so we are in terms of y. So remember, as I said before, I'm going to pay attention to the shape that I'm forming. So this time I'm going to form squares. So the area of a square is side squared. But my slice is going to be perpendicular to the y-axis. So this is the bottom. Let's draw a square. It's important. And this segment right here that I'm coloring corresponds to this segment right here. It's one side of the square, and this time the person would be standing up here looking this way to see the square itself. So I'm going to accumulate a series of area of squares, but we're in terms of y, so in terms of y it's low to high. That's one way to remember how to find your bounds, in terms of y from low to high. So in this case, the lowest y value of the graph is a 0. The highest y value of the graph is a 4. I'm keeping my eye on the formula area of a square, which is a side squared, so I don't have any coefficient out front this time. I need to know the length of that side. And when we talk about the length of the side, I'm talking about right here. So it's going to be the right side minus the left side. So I'm going to need my equation in terms of y. So I have y equal negative x plus 4. When I get x by itself, I'll have x equal to, subtract the 4 and divide 4 minus y. So that is the equation of the line in terms of y. So the right side is 4 minus y. The left side is 0. So the length of the side is 4 minus y. I have to square it because that's my formula for the area of a square, dy. One more step would be 0 to 4, square the binomial, 16 minus 8y plus y squared, dy, dot, 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 FTC part 1. All right, so that gives you 3 examples, and now you can hopefully set up the other problems that you have to do, and if you get stuck or have questions, if you're in my class, I have posted answers. I don't think I have a video of me doing them, but maybe I'll make one, and you can ask me in class.